Hi everyone and welcome to my YouTube channel Math Puzzle with Q. Today we are going to analyze an interesting math problem brought by the channel Mind Your Decision that I'm thanking for this video. And the problem is about the probability of choosing three different numbers in such a way that these three different numbers will be ordered in ascending order when you choose them. And by the way, I warmly recommend their YouTube channel that is full of interesting trick questions like this. So you can find the video that is actually a story in the description. So let's formulate the initial problem. You have three numbers that we can call x, y, and z that all belong to the set of integer 0, 1 to 9. And you want to know the probability that when you randomly select this number, you have x that is strictly lower than y, that is strictly lower than z. So to solve this problem, what they noticed is that for an unordered set of three different numbers, there is only one way to order this set in ascending order: x lower than y lower than z. And the second thing that they noticed is that the number of unordered triple of different numbers in that specific case is equal to 10 choose 3. 10 choose 3 is equal to 120. And because you have a total number of choice for x, y, and z that is equal to 10 multiplied by 10 multiplied by 10, so 10 to the power of 3, the final answer is equal to 120 divided by 1000, which is equal to 0.12, or 12% chance to have your three integer ordered in this way. So the first thing that I would like to do is to generalize this case. So in that case, we have three integer, and each of these three integer can take 10 different values. But we can actually generalize this problem by choosing a k integer that can have n different values. So let's see what we have here. So let's say that we take x1 to xk that can take value between 0, 1 up to n minus 1. What is the probability that x1 is strictly lower than x2, etc., up to xk? Well, in that case, the number of unordered set of different value is equal to n choose k, and the total number of possibility is equal to n to the power of k. So at the end, your probability that all of your x1, x2, etc. will be ordered in ascending order and distinct will be equal to n choose k divided by n to the power of k. We can actually reformulate this formula by writing that n choose k is equal to n factorial divided by n minus k factorial multiplied by k factorial. The probability will be equal to n multiplied by n minus 1, etc., multiplied by n minus k plus 1, divided by k factorial, and multiplied by n to the power of k. Let's have a quick note on certain value of k. For example, if you consider a value of k that is equal to n, what's happening? Well, in that case, you know that n choose k is equal to n choose n, which is equal to 1. And that makes sense because the only way to order the variable x1, x2, etc. is to choose a value of 0 for x1, 1 for x2, etc. up to n minus 1 for xn. Another interesting note is what happens when k is strictly greater than n. by convention, we say that n choose k in that case is equal to 0. And that actually still makes sense for our problem, because if k is strictly greater than n, we choose too many different numbers that can only have a limited number of values. It's impossible to make sure that each of the n integer will be strictly greater than the previous one. And so in that case, the probability will be equal to 0. So now what I would like to show is an alternative method that will come to the same result, but we are going to calculate things in a slightly different way. So let's assume that we have only two integers x1 and x2 that can take n different values, so from 0, 1, all the way to n minus 1. And we are going to calculate the probability that x1 is strictly lower than x2. To do this, we are going to associate the index I to the value of x1 and the index j to the value of x2. So this probability is equal to the sum of all the possible values that j can take from 0 to n minus 1. And note that x1 can only have a value that is strictly less than j. So we need to use another sum for I that can only go up to j minus 1. And the number of things that we count is all the time like only one situation. And we divide everything by the total number of possibility that is equal to n squared. So this sum is equal to the sum of j equals 0 to n minus 1 to the sum of I equals 0 to j minus 1 of 1. So there is exactly j term in that sum. So the total of that sum will be equal to j, and we divide by n squared. And so for those who know this type of sum, we know that the final result is equal to n multiplied by n minus 1 divided by 2 and also divided by n squared. So at the end, you recognize that we have n choose 2 divided by n squared, which is similar to the result that we were obtaining earlier. Another side note on this is that if we want to visually represent the set of values that we are choosing, you can consider this graph here, where I'm representing x1 here, x2 here, and we can choose all the value between 0 and n minus 1. And so all the set of possible value for x1 and x2 is represented by this square, and the set of possible number for which we have x1 that is strictly lower than x2 is represented by this kind of square here, and all the possible values are represented in this area. And this area is equal to n multiplied by n minus 1 divided by 2. So now it will be interesting to see what happened in the continuous case. What I mean by the continuous case is that in that case, x and y are supposed to be independent and identically distributed variable, and we are also going to suppose that they are uniformly distributed between 0 and n. So in that case, what is the probability that x is strictly lower than y? To answer this question, we are going to use a similar trick that we were showing with the discrete case, with the sum. But of course, because we have continuous variable, we cannot use a sum. We have to use an integral, and that probability is equal to the integral for y equals 0 to n of the integral for x equals 0 to y of the probability density function fxy xy dx dy. And because we assume that these two variables are independent and uniformly distributed, we can represent all their value on this square, where we have x here and y here. And the density of this square at any given point is equal to 1 divided by n squared. Therefore, this probability is equal to 1 divided by n squared of the integral from y equals 0 to n of the integral from x equals 0 to y of 1 dx dy. So this part of the integral, as you can recognize, will be equal to y. So we have 1 divided by n squared of the integral for y equals 0 to n of y dy. And we have 1 divided by n squared of y squared divided by 2 between 0 and n, which is equal to 1 divided by n squared multiplied by n squared divided by 2. The first thing that we can notice is that this probability is very similar to the probability of the discrete case that we have seen here. The only difference between the two is that in the continuous case we have simply n squared on the numerator, and in the discrete case we have n multiplied by n minus 1. Another interesting thing that we can notice is that this can be simplified by eliminating n squared, and the probability will be exactly equal to 1/2. And we can see why this is the case when we represent the equation x equal y here, and noticing that this area is the set of feasible situation. This is exactly half of the area of the square. So now let's generalize to the case where we don't have only 2 but k variable. So we are going to introduce x1, x2 up to xk, still independent and identically distributed, and we assume that they are also uniformly distributed. And we are going to calculate the probability that x1 is strictly lower than x2, etc., strictly lower than xk. And here we just have to use the same trick that we use for the case of 2 variables. So we are going to integrate from x k is equal to 0 to 1. So we use 1 instead of n because we have seen that the result don't depend on n, so we can assume that they all take value between 0 and 1. Integral from x k minus 1 equals 0 to xk, etc. 1 dx1 dx2, etc. to dxk. So for this case of k variable, we can show that what is going to happen recursively is that we're going to have this that will turn 1 into the integral variable that will be u, that will be turned into u squared divided by 2, being turned into u cubed divided by 3 factorial, etc., all the way up to uk divided by k factorial. And since we integrate between 0 and 1, this is going to give 1 divided by k factorial. And this is the probability of having the k integer ordered in that way. So of course the formal proof goes a bit slower than that. Sorry for going so quick on that step, but you can basically prove this by induction over k, and please let me know in the comment if you have a more formal proof that you would like to show. So now it will be interesting to compare side by side the discrete case and the continuous case. So in the discrete case, what we have is that the probability that x1 is quickly lower than x2, etc., up to xk, when all the xi take value between 0 and n minus 1. So this probability is equal to n minus 1, n minus k plus 1, divided by k factorial n to the power of k. And when we have xi that takes any value between 0 and n minus 1, and as we have seen, it actually doesn't depend on n, we can have between 0 and 1, this probability is equal to 1 divided by k factorial. Something that we can notice is that in that numerator, we have k term, and we have n that is lower than n minus 1 that is lower than n minus etc., n minus k plus 1 that is lower than n. So we can say at the end that this probability is lower than n to the power of k divided by k factorial and multiplied by n to the power of k. So this can be simplified, equal to 1 divided by k factorial. So in conclusion, what we can see is that the discrete case, the probability is always lower than the continuous case. And so to explain why this is happening, let's imagine that you have your xi that belong to 0 all the way to 9. So we take n equal 10. In the discrete case, if you choose, for example, xi equals 7, xi minus 1 can only take value that are equal to 0, 1, all the way to 6. But that's it. And so you have 7 possibility divided by 10 initial possibilities, so you have 70%. But what happened to the case where xi is continuous? Then you have xi minus 1 that simply needs to be lower than 7. So you can choose up to, you can choose from a range from 0 to 7 divided by a range from 0 to 9. This is equal to 7 divided by 9. That is approximately equal to 77.8%. So as you can see, this number is greater than this number. And this is because in the discrete case, we actually eliminate much more situation than in the continuous case.